All right, so I'm gonna go ahead and make a little series, just a small series of videos that'll hopefully help you through your summer assignment and give you just a little bit of the review over the stuff that you for sure had to have pre-AP year, and you're going to be applying it right on day one. So I'm going to try and review all of that. I know our boot camp sessions, we're having a hard time scheduling those. So worst case scenario, these will be the videos that you're going to rely on, and then I will be available for tutoring before school starts if you need that. Otherwise, just use these and email me, message me questions, whatever you need, okay? So to get us started, like I said, I'm going to start from page 1, which I know there's a video that I had already offered to you with this. So some of you guys can probably skip this entire first video, just kind of skip through. I do 1 through 8 on this first one. But to start us off, this very first question that we've got, it's giving us a little density column, and it gives you the list of everybody's densities, which we remember is grams per milliliter, okay? And basically when you have these density columns, the more dense things are going to be at the bottom, less dense is going to be on top. Pretty easy stuff. Water, I was not supposed to give you this value, but I gave it to you. So water, you do need to have that memorized as being 1 gram per milliliter, because they like to give you water as one of your options so that you have a basis of where everything else goes. So make sure you always have that one memorized. But we know that whatever is going to be above water has to have something less than. So that limits us down to this guy and this guy, okay? So now you got to use your brain a little, and we're going to go ahead and we're going to look at what these two people are. So we've got hexane and we've got ethyl alcohol, okay? So when you have your hexane, and one of the things that I will be having you memorize is all your anes, at least, okay? And there's an easy way to remember it. But what I want you guys to know for now is that whenever you have any of these kind of anes, you have a carbon chain that is surrounded with a bunch of hydrogens, okay? And so looking at this little shape here, you can kind of tell, is there any off balance or any imbalance, I'm sorry, of the symmetry on this? And there's not, it's perfect. So when you see that, you should be telling yourself, is this a polar molecule or is this a non-polar molecule? This has no poles, so this is going to be non-polar, okay? When you have something like ethyl alcohol, a lot of your alcohols have this little OH. So they have this big fancy thing over here with C's and H's and O's. And then you have an OH that's usually tagged off on the side or on 2 sides. Okay. And so because of that, you can tell that this is going to have its own charge kind of pulling one direction. The other guy is going to be pulling the other direction. So this is actually a polar molecule. It's not going to be a balanced molecule. So looking at these two facts, now you have to go back and know what you got to know about water, which is that water, okay, probably don't have to draw this for you, but just in case, water, you can see, has a partially negative side and a partially positive side. So this is a polar molecule. One of our rules about dissolving and miscibility is that polar dissolves polar, and nonpolar and polar things usually don't mix, okay? So knowing that, which is the only one that would actually show a distinct layer? And that would be your nonpolar guy. So this is going to be hexane. Because if we were to pour alcohol into it, the water and the alcohol would just mix together. All right, and then finally, liquid 3 is between water and mercury. So we know it's above 1, which is everything. And then it's below what mercury is, which is 13.5. So it has to be between 1 and 13.5. We've got 3 contestants here, okay? And what I want you to notice is that this first one, this methane guy, he's just so close to 1. So there's really, if you have that close of a density, you're not going to have this huge layer. So if we had to deduce it down to something, I would probably eliminate this guy because he's just so close to 1. So when we look at the aluminum or the bromine, okay, they both look like equal contestants here, okay? But you have to remember that in this sentence, they are telling you that they are at room temperature. And I think we've all seen aluminum foil before in our life, and that thing does not melt if you store it in your cabinet at room temperature. So aluminum exists as a solid in room temperature. So we're not going to have, obviously, a solid. This is a liquid. So bromine, if you remember looking at the periodic table back in pre-AP year, especially on my periodic table in the back of the room, you saw that it had blue. Right? So it was written in blue letters, and that's because it is actually liquid at room temperature. So your last little guy is going to be bromine. Okay? So on this question, I was reminding you about density. Okay, your density column, what that means. Your polar versus nonpolar. I've introduced that you are going to be memorizing your anes. And that there's a really easy way to do that, like I said. And you're recognizing that alcohol usually means that it's a polar molecule. It has this extra little OH tagged onto it. And we reminded you about the polar dissolving polar things. Like dissolves like. Okay, so for question number 2, now we're bringing in vocab, okay? So we have accuracy and precision, okay? And we know that accuracy, when we're looking at our little bullseye examples up here, is right. Okay, so when you're looking at right, or when you're looking at what accuracy is, you're looking at how close is it to what it was supposed to be, right? And so when we look at our bullseye here, we're looking for somebody to get as close to the center as possible, because that's what we're usually trying to aim for. When you are looking at precision, okay, or being precise, okay, precision is talking about how good your tool works, basically. All right. So if you're doing if you're using the same tool and you're using the same method every single time, you know, it doesn't really matter how close you got to it, as long as your measurement should always be coming out to be close to the same thing. If they are not, so let's just say you were using electronic balance in class and you're measuring the same piece of metal, and the first time it was 5 grams, second time it was 7 grams, third time it was 4.8 grams, then, and you know as a scientist that you did everything exactly the same, then obviously that scale is wrong, and it's not showing good precision. And so that's usually a big indicator that you should probably get a new balance. But anyway, so when you guys are going to do your labs this year, a big thing that you want to look for is you're not always going to get exactly what was expected. Okay, high school labs, we've got a lot of room for error. But what I do want you to always be looking for are your measurements precise? Okay, if you do more than one trial, are you using the correct method to make sure that no matter what, you've got that? Because most likely, we're going to be doing a before and after measurement in a lot of your labs. And so if we do that, as long as you are precise, you're still going to have the same difference as if you were accurate. And that's why that's so important. So when we're looking at our bullseye, it's going to be when they are grouped together, okay? So looking here, which measurements are precise? I would say B and C. Which measurements are accurate? That's going to be C. Those are right where they need to be. Which ones are both precise and accurate? And that is going to be C, okay? So I guess this one probably wasn't up there. And as you can see, A is all over the place. There's something wrong with whatever was throwing the darts at that bullseye. Okay, or target. Number 3, it says explain the difference between an exact and an inexact number. So I'm just going to kind of give myself some room here. All right, So exact versus inexact. What you need to know is that with exact numbers, we don't care about SigFigs. Okay? These are counting numbers. So if you were to look into a room and say there's 15 people, you can't cut any of those people in half. You can't say, oh, there's 2 arms, so we'll say 15.2 people. No, like counting numbers are exact numbers. There's no SigFigs. We can't say 15.0 people because there's no way to actually say that. Okay, when you're counting, you use whole numbers. Okay. You also use exact numbers when you are in the same system. So, for example, if you're going from metric to metric, system. So if you're going from metric to metric, you are going to be using this exact number, this exact conversion, okay? If you are an American system and you're going to American system, there's an exact conversion for that, okay? Inexact numbers are going to definitely use your SigFig. So it depends a lot on what your measuring devices are. These are going to usually have decimals, okay? And it's going to be when you're in different systems. So looking at, that's your answer for number 3A. 3B, for each case and K, which one is exact or inexact? So the number of faces. So looking at a room, you can't cut anybody's faces in half. So we got exact. Okay. The mass of 6 apples. Mass is not always a whole number. So that's going to be an inexact number. And your decimals depend on what tool you are using. How far does it go? Okay. The number of seeds in an apple. I know sometimes we get half a seed, but this is actually going to be an exact number. So once again, it's a counting number. Number of feet in 1 mile. So this is where you got to look at, okay, so you know it's a conversion, okay? Are we in the same system or are we changing systems? Both of those are in the American system. So this is going to be an exact number. And then the number of liters in 5 quarts, we have metric, which is liters. That's what you guys are going to be using all year. And quarts is American. So we have an inexact. Okay, so we've done accuracy and precision. We remind you of that. Exact and inexact. Okay, so now for our SigFigs. So I'm going to take a minute or so to remind you of your SigFig rules. So the easy ones are just knowing which ones are significant, okay? So, and then we have our actual, when you do math, what are the SigFig rules for that, okay? So how to recognize which ones are. Non-zero numbers, always, okay? Your second rule is all about those zeros. Okay, so point number 1, zeros will be significant if they are sandwiched. Okay, meaning if I have 102, this guy counts. If I have 0.102, this guy counts. Leading zeros never count. So back to the example beforehand, this guy does not count, okay? Leading zeros, we call them placeholder zeros. And so what that does is that we could use scientific notation. Scientific notation is, if you remember, that was when we did like 3 times 10 to the third. And that would tell you to move that decimal over 1, 2, 3, right? We can go backwards and have a -3 and go 0.003, okay? But no matter what, these guys don't really matter because I could change it back to being what it needed to be, Okay, I can change it with scientific notation. So those guys are actually, they never count. Okay, so in this number right here, none of these count. Okay, trailing 0 with no decimal. I like to actually stick this under the sandwich rule, but I want to tell you this one just in case that doesn't make sense to you. But if you look at these 3 zeros here, once again, they are placeholders. So we can just move it however we want using the scientific notation. They don't really count. If you look, the only number that counted up here was the 3. So these guys do not count unless I put a decimal at the end. And if you put a decimal at the end, that leads me to my next thing, which is that this last rule comes into play because, once again, it is judging you on what device you are using to make your measurements. Okay, how accurate does it go? How precise does it go? All right, how it's accuracy actually. So how accurate this thing goes. If you're looking at two measurements, most of us have done this example before, where you are measuring in a beaker versus a graduated cylinder, right? We know that this graduated cylinder has a lot more lines than our usual beakers do. So if we have something that's about right here, and let's just say this is a 200 milliliter, right? So this says 200, this says 100. Looking at this, okay, we can only estimate one decimal place on here, okay? Which means we can only estimate this guy. So looking at this, we can say, oh, that looks like about 150. On these over here, if we have, let's just say it goes by 20s, okay? So 20, 40, 60, 80, 100, okay? And let's just say it's in between here. We can guess this guy, which is 65. If you look, this is the ones place. We only got to guess to the tens place on this one. So that's why those trailing zeros, it's really important to keep track of that, okay? If there's no decimal, then you're only allowed to know what that first digit is, okay? You're only as accurate as your least accurate device, okay? And so just make sure you're paying attention to those trailing zeros. All right, let me give myself a little bit of space here. And now we're going to talk about the math rules real fast. So while I'm erasing, so the math rules come down to you are either adding and subtracting, or you're multiplying and dividing. And you do follow PEMDAS, which is the order of operations, okay? You always start with your parentheses first, then you go into your exponents, then you do multiplication, division, and then you end with addition and subtraction. So you're still going to follow that, but you're also going to follow your SigFig rules within that, which that's where a lot of people get tripped up. So when you're doing math, okay, when you are adding and subtracting, okay, adding and subtracting, you're going to use the number with least decimal places. And that goes back to what I just kind of explained, where if you add a beaker with a graduated cylinder, you can only be as accurate as that beaker, because that is the least accurate device out of those two. And so when you're adding and subtracting, you can't throw in that extra ones place, okay? Okay, so you're going to use the least number of decimal places. Let me put the number sign in here. So for example, if I had 1.02 and I'm comparing it to something that was 1.1, I could only use this one. And furthermore, if I had something that was 10, okay, notice he doesn't have anything. It's a whole number. So you can't have anything actually after the decimal. Okay, so if you had to add all those together, you'd have to follow the one with the least number of decimal places. All right, the second rule with multiplication and division is you use the number with least number of SigFigs. Okay, and so and I'll show you that in a couple of these examples, but it's going to come down to making sure you can recognize which ones are significant, which ones are not. Okay, okay, so what I'm going to do is we're going to just kind of run through these. I'm not going to do the math for you. I'm going to go ahead and have you do it, and I'm going to leave the last one to you so that you can figure out a little bit. So this first one, we have what going on in general. We have a subtraction. So we're going to follow this first rule. So we're going to look at the number of decimal places. 0.347 has 3. 0.0732 has 4. You're going to only be able to have 3 decimal places. Okay, so when you do your calculation and you type it into the calculator, you make sure you round to 3 decimal places. So you should have something like 0. And you're going to have 1, 2, and 3. So this will be the number to round, depending on that guy. Okay? Okay. Looking at the next one, we have, I believe that's addition. If you say it's division accidentally, that's fine. I don't care. But I'm going to go ahead and go with addition. And so here we're going to look at our decimal places again. I have 3 here. I only have 1 here. Okay? So your answer can only have 1 decimal place. Our next one, we have multiplication going on. So I'm going to change my color here. And multiplication, we need to make sure we are using the least number of SigFigs. So we got to count SigFigs. So all non-zero numbers are, so 8.25 has 3 significant figures. 0.14, okay, we have 2 non-zeros, and then we got to look at our zero rules for a second. Leading zeros never count, so that 0 up there does not count. So this only has 2 SigFigs. So your answer can only have 2 significant figures. Notice we're not following decimal place anymore. Okay. For the next one, we've got division going on. So again, you're going to count. So 0.834 has 3. And so 0.834 has 3. 12.45 has 4. So when you go to actually calculate this in your calculator, your answer can only have 3 significant figures. All right, and last one. Okay, this is what's going to happen to you a lot. I'm just giving you the warning. When you have multiple things that need to happen, for now, I need you to run through each of the operations in the correct order. So once again, you're going to be following that PEMDAS, which is parentheses, exponents, multiplication and division, addition, subtraction. Okay, so looking here, your first thing that you have to do is going to be your parentheses. So you're going to do a subtraction. So your subtraction rule is that you can have 3 decimal places. Okay, so you're going to type that in your calculator, get a number. You can only go to 3 decimal places. Your next thing you're going to do is going to be division. So looking at that, you're going to have to look to see how many significant figures you have on top and how many significant figures you have on bottom. You go with the lowest number. And you're finally going to be adding it to the 2.091. So once again, you're going to be looking at your decimal places. So this is 3 steps, and I want you to give it a try. I will post the answer. If you want to ask questions, you can do that. And if I need to upload another video to kind of walk you through that, I don't mind. Just let me know. All right. Number 5. So this was an interesting question. So this is using density again. So we remember density is your mass over volume. Okay. And they tell you that you have this concentrated sulfuric acid, which has a density of 1.84 grams per milliliter. Okay. Concentrated sulfuric acid is only 95% pure sulfuric acid. So when they say that, they're saying that this grams per milliliter, they only want 95% of that 1.84. Okay, and that's actually what pure sulfuric acid, or that's how much pure sulfuric acid is needed. Okay, when we talk about concentrated sulfuric acid in the lab. So what volume of concentrated sulfuric acid contains 100 grams of pure sulfuric acid? So there's two ways to do this. I'm going to show you the dimensional analysis way. You can also do it in a proportion. Okay. Dimensional analysis way says I need to know what 95% of my original thing is, because what we're saying is this is it if it was 100%. Okay, so what is only 95% of that? Okay, so if so what we're going to do is we're going to multiply it by 0.95, and you're going to get something around 1.75. I don't have a calculator on me right this second. Grams. Okay. And so knowing this, you can now use this 1.75 grams per milliliter, and we're going to go ahead and go back to what we want to get to. We want to know volume. So I'm going to say, all right, I have 100 grams of sulfuric acid that needs to be used. So we're going to bring words down to the right. Okay. And we want to get into volume, which I know is milliliters. Well, we have something that is grams over milliliters. I know it looks upside down, but you can use that. You can always flip those things. So we have 1.75 grams per 1 milliliter. And that will actually get you your answer as well. The other way to do it, like I said, you could have also done a proportion, which some of you guys are going to prefer, but I do need everyone to start being very comfortable with this. Use your railroad tracks, use your dimensional analysis. My people coming from physics, hopefully that's something you've been practicing all year. My people coming from pre-AP, you did stoichiometry last year. It's the same exact thing. You're going to be using this constantly, and to have this scale or this skill is going to help you immensely, okay, with a lot of these little multiple choice questions that AP likes to throw your way. So make sure you get this skill. But if you solved it the other way, there's no shame in that for now. And that is that you said 95 is to 100, right? So 95% versus 100% is the same as something to 1.84, okay? And this would have gotten you your 1.75 grams per milliliter. And then you could have taken 1.75 grams per milliliter, set it up to be mass over volume, which is 100 grams over volume. When you're solving for the bottom guy, switch the two out. Okay, so you could have done either way here. The proportion or the dimensional analysis. Like I said, dimensional analysis is definitely something you're going to have to get used to, though. All right, on this page, I am actually not going to go through number 6 because I feel like you guys are very capable of looking these words up. Don't stress too much over this guy. We will talk a little bit about paper chromatography. When you go to look it up, I know they're going to say things like like which ones are fast versus slow flow rates and stuff like that. But what I want you to focus on is that when you use paper chromatography, okay, your liquid is something and your paper is something. And it all comes down to solubility rules, which is something that you guys have to memorize, okay? And so if it's soluble, right, it'll flow through. If it's not, it's going to stay put. And that's what I want you guys to get from paper chromatography. The other ones shouldn't be too bad for you to look up. There's plenty of examples out there. If you have trouble with something, just let me know. And I will cover it for you. All right, so now the separation of matter. All right, so we've got matter is the big guy here, okay? And then I wanted you to fill in the rest of the words. So what it comes down to is matter is separated into pure substances and mixtures, okay? Mixtures are things that can be separated physically, okay? Excuse me. Pure substances are broken down into either elements or compounds. So for example, if I have a glass of water, right? Okay, that is a pure substance because they're all a bunch of H2Os. Okay, but they're not an element, right? It's a compound, but all of it is uniform throughout. Something like element would be a container of oxygen gas, okay? When we have mixtures, you have two different categories on this. You have homogeneous and heterogeneous, okay? Homogeneous means it's uniform throughout. Heterogeneous means you can see chunks. So when we say that one of them can only be separated chemically, that's going to be your homogeneous, okay? And most likely, you're going to be using something like evaporation or distillation for your homogeneous things. Your heterogeneous things, where you can see chunks, you usually can use decantation and filtration, okay? Paper chromatography is just its own little category. Usually it's for your homogeneous as well. All right, so heterogeneous. And I know I didn't give you any more squares, but let's go ahead and actually categorize the last three words. All right, homogeneous. Those things we call solutions, okay? So you can have an alcohol-water mixture solution. So if you've ever looked at rubbing alcohol or your parents' little alcohol cabinet, you can see that a lot of things have percentages on them, whether it's like 45%, 75%, whatever it is. That's what they're talking about, is they're talking about how much alcohol is mixed in with that water, okay? Your suspension and colloids, these guys are going to be over here. So colloids are heterogeneous. However, sometimes the colloids, something like milk, or your little smoke, which is solids suspended in the air, they do have a homogeneous characteristic sometimes, but we do categorize them as heterogeneous. Okay, and this is our last one, number 8. So number 8, you're going to have to really get comfortable with particle diagrams, okay? Particle diagrams, you're going to be asked to draw them a lot. So it's all about orientation of your molecules and how are you going to show a homogeneous mixture versus a heterogeneous mixture. So this is kind of prepping you a little for that, making your eyes kind of see to that atomic level. So these are all showing atoms and molecules, okay? So you're looking zoomed in. When you have a mixture of two, you got to see, hey, do they look off balance? Do they look pretty symmetrical? There's a lot of answer choices that are going to be, they're arguable, and I'm okay with that. As long as you can back it up with evidence, I usually accept your answer on it, okay? But I'm going to go ahead and tell you how I interpret these pictures. All right, so letter E. We've got something that looks like Mickey Mouse faces. So I'm actually looking at this and I say that looks like a bunch of water, okay? So the first question is saying, is it homogeneous, is it heterogeneous, or is it a pure substance? These are all the same things. So I'm going to say this is a pure substance. I'm going to put PS, okay? Question number 2 is asking, is it an element, is it compound, or is it both? Looking here, there's nothing that's elemental. They're all compounds. So I'm going to go ahead and put C. Number 3 is asking for, let me actually make this a little bit bigger. I'm going to run out of room. Okay. Number 3 is asking for, is it a solid, liquid, gas, or a combination? So that's where you got to kind of use your brain a little and your imagination a little. And I look at these and I think they're very organized, right? You have a whole row here. You have another one sitting on top. They're very organized. So I would say it's a solid. Okay, I would say solid. I've had people argue it's a liquid because there's that one extra guy that's sitting up there. But when I see something so organized, I imagine a solid. Okay, your gases are going to be pretty spread out. Your liquids are going to be a little lopsided, if you can kind of imagine that. And then you will have combination. We'll look at those on the first day of school or first or second day of school. Okay. All right. Letter F. Okay. Once again, I have all the same guy. So I'm going to say this is a pure substance again. Okay. Is it an element, compound, or both? They all look like it's one atom. So I'm going to say it's an element. Number 3 is asking solid, liquid, gas. I think it's very organized again. So I'm going to say solid. If you argue liquid, I would probably accept it. Okay, as long as you can back it up as to why you're saying that. But once again, I think if they're all on level with each other, there's no lopsidedness, then it's a solid. All right, letter I. I look at this, and they're all the same characters, so I'm going to say pure substance once again. Oh, let me do that back in pink. Okay. Number 2, element, compound, or both. These are elemental. And this is where I see kind of the waviness. So I'm going to say this is a liquid. Okay. All right, J. So here we actually have 2 things now, right? We have this character and we have this character. Okay. This is something we call a diatomic molecule. So something like oxygen is a diatomic molecule. Make sure you have your diatomic 7 memorized by the first day of school. And your diatomic 7, just a reminder, you have hydrogen, which is over on that side of the periodic table, and then you kind of go over and you make a little 7 on your periodic table, which will be nitrogen, oxygen, fluorine, and then you go down, you have chlorine, I'm doing this all by memory. Bromine, iodine. I think iodine was supposed to be up there. But here you have 1, 2, 3, 4, 5, 6, 7. Okay. And so that's your diatomic 7. Make sure you always remember, no matter what, they have to exist in a diatomic molecule. They don't exist on their own in the natural world. All right. Anyway, so that's a diatomic molecule. And then we have this little compound. So I'm looking at that and I think this is not, actually, you do have to think a little bit harder. So homogeneous versus heterogeneous. So I know it's a mixture. I know it's not pure substance. People argue this different ways. What I see when I look at this is that there's a little line right here. If they wanted it to be homogeneous, then these 2 maybe would be swapped, right? So I'm going to call this actually a heterogeneous. So I'll put hetero. Okay, because it almost could be like a density column where you have 2 different layers, all right? Number 2, element, compound, or both. I see elemental things and I see compound things. So this is going to be both. And then finally, solid, liquid, gas, or combination, they look kind of all over the place. So if you really... as long as you aren't saying solid, I would be okay with that. And probably not combination. You don't really see a distinct 2 things. But liquid or gas, I would accept. Okay. So hopefully this helps you with the first 8 and expect another video very shortly. Thank you.